Today it's our pleasure to have Adel Javanmard as our speaker. Adel is an assistant professor at the USC, and now you can guess how get to know each other and actually start collaborating. So Adel has worked on statistics, machine learning, and also optimization, and he got a lot of awards, including the Thomas Cover Dissertation Award, and also Google Faculty Research Award, and also he also got nominated for a Student Paper Award, ISIT Student Paper Award. And today he's going to talk about dynamic incentive-aware learning, which is a robust learning approach in contextual actions. Please join me to welcome Adel to our session.
Okay. Thanks for the introduction, and thanks for inviting me. It's a great pleasure to be here at Google. So as Negin said, I'm going to talk about dynamic incentive-aware learning, and this is based on joint work with two fantastic collaborators, Negin and Wahab. Both of them are here. So the plan is that I will give the talk, but if you have hard questions, you can ask them. They know the stuff better than me. Okay, to set the stage, let me start by the online markets. These are the platform that connects the buy side to the sell side of the market. And living in the era of data deluge, we are easily gathering massive amounts of fine grain, not only on both sides of the market, but also on the items that are going to be sold in these online marketplaces. And because of this fine grain information, the items to be sold are getting highly differentiated. And also you are dealing with heterogeneous customers. So for a single item, different customers will value it as different. So we have both heterogeneous customers and also highly differentiated products. And the seller wants to leverage this contextual information to optimize the prices. Now, this features, the heterogeneous and contextual market, has its own challenges as well. So let's get back to the question that how do you want to set the prices? The typical approach is that you use the historical data and try to learn what are the optimal price. But the challenge is that in many of these markets, you have frequent interaction between the buy side and the sell side. And so the buyers have incentive to manipulate the seller in order to get lower prices in the future. And so you are dealing with the strategic buyers. So for this work, we were mainly motivated by the display and ad markets. And in these markets, the sellers are the web publisher, the buyers are the advertisers, and the items are the impressions or the ad views. And it has all the main features that I was talking about. You have the contextual information because buyers, the advertisers, have access to the HTTP cookies for each of the users. You have heterogeneous markets because each of the advertisers in market would target some of the users, and this targeting depends on the preference of that specific advertiser. So you have heterogeneous buyers in the market. You have a strategic player in the setting. Everyone wants to maximize their utility, and so they are not necessarily truthful. And also the fourth feature is that you are getting repeated interactions between the both sides of the market. Okay. Now, one of the popular auctions that are used in these markets are the second price auction. And these auctions are also very interesting in theory. So this is what I will spend more time later on the second price. And the goal of our work to set it just vaguely and broadly is to design a low regret pricing policy for the seller. So we are just looking at the problem from the seller's perspective. And we want to be robust against the strategic buyers. Of course, I need to define the notion of regret, robustness, but overall, this is what we want to do. Any questions so far? Okay. So this is the outline of the talk. I will go with the model, and then we discuss two pricing policy. One of them is called CORP. It's the acronym for Contextual Robust Pricing. And the second one is SCORP. So these two are defined for different settings. And I will conclude with the takeaway messages. Okay. So let's go with the model. We have n buyers, and at each time you have an item to be sold. So you get one item each time. And the item is represented by a large dimensional feature vector xt, so it's in d dimension. The features xt are drawn IID from some unknown distribution. So you have this stochastic assumptions on the features. You observe the features, the seller and buyers, both of them see the item, so they observe the features, but they don't know what distribution these are coming from. And then each buyer has a valuation of this item. And this is private knowledge to that buyer. The other buyer doesn't know this valuation, and the seller also doesn't know this valuation. And then you want to sell this item through second price with reserve.
So you're assuming that each single buyer will recur throughout time, right?
Yeah.
All the same end buyers will recur throughout time.
Right. And we want to sell the item with the second price auction reserve. And reserves here is to preclude the allocations when the bids are very low.
So the evaluations are related to the context in some way?
So we'll get to that.
There are some function of the context. Okay.
So this is the pictorial representation of the setting. You have a seller and you have n buyers. Here I have 4 buyers. And then at each time you get a product. So let's say it's an ad view you want to sell. And then the seller set the reserve prices for each of these buyers. So you have R1 to R4. And then sends the contextual information, XT, of this product to the buyers. Now, after they see this XT, based on the valuation that they have, they submit their bids. And the bids are only known to that bidder and the seller, so the other buyers doesn't know the bids. And then the seller would run the second price with reserve. So the winner would be the one that has the highest submitted bid if the winner clears the reserve. And the payment that the winner pays would be the maximum of the second highest bid and the winner's reserve. So this is the lazy version of the second price. Now, second price auctions are widely used because first, they are very simple, and second, they are truthful. So one dominant strategy is that everyone wants to just beat their valuation, and there's no incentive to deviate from that. But when you look at this problem over multiple rounds, when you have repeated interaction, then the second price auction is not truthful anymore. So it might be the case that the buyers want to sacrifice their short-term utility in order to game the seller and get lower prices in the future. Okay, so this is the main challenge that exists in repeated auctions. Okay. So that was the first part of the model. The second part is that how the buyers would evaluate the item. So this is based on your question, how it depends on the feature vector. So the valuation of buyer I at time t, VIT, would be a linear form of the feature. So it's xt times beta I. And beta I here is like the preference vector of that buyer, how that buyer would weigh different features in the valuation. And ZIT is the noise, it's the market shock. So the preference vectors beta I are unknown to the seller, but the seller can try to learn them over this repeated interaction with the buyers. And for the sake of normalization, we are just assuming that beta I are bounded by some arbitrary large constant, and xt is bounded by 1, the null. It's just a matter of normalization. And here, the market shock VIT, of course, are not observable, and they capture the features that are not measured by the seller.
The valuations could be negative.
The valuations could be negative, but then, it's just 0.
Do you know the distribution of the market shock?
Okay, very good question. So we'll get to that one. So the market shocks are coming IID from some distribution. So F here is the CDF of that one with a bounded support. And the technical assumption that we have is that F and 1 minus F are log concave. So we'll get to the part that we need this assumption. And I tell you when you should recall this assumption. But what I want to highlight is that
the PDF is log concave or the CDF is log concave?
There's a theorem that if CDF is log concave, then the PDF, if the PDF is log concave, the CDF is log concave, but not vice versa.
Yeah. So which one you are assuming? You're asking.
So all of these, the CDFs are
Okay.
log concave.
Particularly if the PF is log concave,
Yeah.
it goes through the log
Yeah.
concave.
And back to your question whether F is noun or not. So we consider two settings. One is that you exactly know what F is, and we define, we propose a policy, the core policy that lends itself very well to the setting. And the other setting is that you don't know F, and then we propose another similar policy called SCORP. So this is a stable core. And the stability here is against the uncertainty in the distribution. Okay. We are still in the model section. So we are assuming that the buyers are utility maximizer. So we are not focusing on any specific strategy for the buyers, but they want to maximize their utility. One important thing that we should note in our model is that the buyers are assumed to be less patient rather than the seller. And this is a practical assumption in many markets. For instance, in the online advertisement, when you target a user, you want to show the ad sooner rather than later. You don't want to wait forever. Or in cloud computing, you just want the capacity when you need that. You don't want to get it after a while.
So it means both the time discount and time discounts are different. Is that the difference?
Yeah. So it means that how to capture this one, when we are computing the cumulative utility of the buyer I, we discount the times over time. So at time t, the utility would be discounted by gamma to t. And what's the utility of buyer I at time t? If it gets the item, so the allocation QIT is 1, then utility would be DIT minus PIT. It's the valuation minus the price. If buyer I doesn't get the item, so QIT is 0, PIT is also 0, so the utility of the buyer would be 0.
The seller is undiscounted?
The seller, no. The
So,
revenue of the seller, no. So this gamma says that over time, buyers are getting discounted utility, but seller, no. So they somehow formalize that buyers are less patient. And then the buyer, as I said, wants to maximize this capital U of I. So before I go to the algorithm, what are the challenges and what are the goals? So to reiterate, the seller's goal is to optimize the reserve price over time. And the seller doesn't know what are these preference vectors of different buyers and wants to learn them through these interactions. And the challenge is that the second price option is no longer truthful when you have repeated interaction between the both sides. And buyers have incentive to manipulate the system by bidding untruthfully. Okay. And the summary of, yes?
Since there are multiple buyers here, are we going to have to worry about equilibrium, or is that are interactions between buyers somehow independent in a way that I'm not seeing?
Yeah, so we've thought about that one to see what are the equilibria for this one, but when you have a dynamic pricing, dynamic mechanism, it's hard to characterize those, but this is not what we are.
So it's not going to matter.
No. Okay, so the summary of contribution is that we have two settings. One is that when you exactly know what F is, so you know what's the market distribution, and the policy that we propose, the core policy, will get a logarithmic regret in terms of T and also dimension of the features. And the second setting is that when the market noise distribution is unknown and you get T to the 2/3 for the regret.
So you get logarithmic dependence also on D.
Yeah. So it's logarithmic in T and D.
So when D is exponential, it's still, let's say D is T is equal to T, that's still sublinear regret.
Yeah.
All right.
And okay, what techniques do we use? So I will explain more on the techniques, but just to give you a heads up. So the challenge, as I said, is that the buyers are a strategy. So we want to come up with a policy that somehow reduce the incentive of buyers to be a strategy. So one technique that we use is that instead of relying on the bids, we only use the censored bids. But this way, the buyers know that their bids is not going to be used directly, but it's only a censored version of that. So they have less incentive to manipulate the system. And the second one is that the policy that we propose has some episodic structure. And when you combine this structure with the assumption that buyers have this discounted utility, you'll see that this episodic structure actually helps you to reduce the incentive of the buyer. So I'll explain this in more details later. Okay. Before we go to the algorithm, I wanted to discuss related work. Of course, the literature on dynamic pricing is very vast. So this is just a representation of the work. And so I've thought about that in terms of 4 lines of research. So in the first one, you have the non-contextual Bayesian setting, that you assume that the bids are coming from some distribution that you don't know, and then you want to see what are the optimal prices to set. In contrast, you have the frequentist model, where you assume that the buyer's willingness to pay or the demand function is coming from some parametric model, and the parameters are fixed but unknown, and then you can use the maximum likelihood estimator or other types of estimator to estimate the parameters of the model. The second line is contextual dynamic pricing. So here, it's for non-strategic buyers, but you assume that the valuations are defined in terms of a regression format. So it's a linear function in terms of the features. And you want to see what are the optimal prices. But again, this is for non-strategic buyers. And closely related to our setting is pricing when you have a strategic buyer and you want to also do learning. You want to learn these parameters. So in the first 3 works, it's assumed that you have strategic buyers that are working with, that are interacting with the sell side, but the first 3 are non-contextual. And the first 2 are on single strategic buyer. The third one assumes that you have multiple strategic buyers, but it's again non-contextual, and the items to be sold are assumed to be ex ante identical. The fourth one assumes a contextual setting, a single buyer, a strategic. So what we add to this model is that we have noise, and also we extend that to the multiple buyers in the market. So in short, I think we have a quite rich model that would be interesting to answer some of this question. Okay, so let's start with the CORP, the contextual robust pricing. So the setting here, just to say it upfront, is that the market noise distribution F is known. So this is the overall representation of the algorithm. It has some episodic structure, and the length of the episodes doubles each time. So the length of episode K, LK would be 2 to the K minus 1. And the seller only updates the estimates from the preference vectors at the beginning of each episode. So whenever a new episode starts, you update your estimates from all the preference vectors, and then you stick with that estimate throughout the next episode. How do you set the reserve prices here? You want to exploit this knowledge. So you set the reserve price to be the optimal one based on the estimate that you have of the preference vector. So we'll get to the formula. But, for the but here, so at each time t, you could also do exploration with some small probability. So if you are at a period in episode K of length LK, the probability 1 over LK, 1 over the length of this episode, you do exploration, which means that you choose one of the buyers, one of them from the n buyers uniformly at random, and then you set the reserve price to be uniformly from 0 to B. B here is the maximum valuation that you can get under your model. And you set the reserve for the other bidders in the market to be infinite. So this is the exploration that you are doing. The prices are uniformly around. But this doesn't have effect on your regret because you are doing that with a small probability 1 over L. Okay. So before I go into the details of the algorithm, let's see what's the advantage of having this episodic structure. So recall that the buyers are less patient than the seller, so they have this discounted utility. Now, let's say you are one of these buyers and you are at this period and you want to submit a bid. But you know that the seller is not going to use your bid to update its estimates until the beginning of the next episode. Okay. So that's the time that the long-term effect of your bid starts to kick in. But you also have this discount factor here. So when you get at the beginning of the next episode, you already have a small discount factor. Okay. And somehow we are limiting the long-term effect of the bids. Now, how small this factor is depends on what period of this episode you are talking about. When we take the average, you see that this episodic structure helps you to control. Okay. So you can contrast this with an algorithm that tries to update the estimate of the preference vector at every round. Now you see that whenever you submit the bid in the next period, it would have some effect on the estimates of the seller. Okay. But that doesn't bring any robustness against strategic buyer. So this is why the episodic structure is helpful. Okay. Now there are two questions about this algorithm. One is that, okay, how do you compute these estimates for the preference vector? How do you estimate beta I? And the second question is that once you have these estimates, how do you set the reserve prices? I just said that you choose the optimal ones based on the best guess that you have. But what's the exact formulation? Okay. So let's start with this first question. How do you estimate the preference vector? Recall our goal. We want to come up with methods that reduce the buyer's incentive to bid strategy. Now, suppose that you can convey a statement like this to the buyers, that their bids are not going to be used in setting their reserve price. And it's good in the sense that, okay, they don't have any incentive to be untruthful because the bids are not going to be used anyway. But we cannot use this approach because the buyers are heterogeneous. So you cannot use the bids from other buyers to learn the purchase behavior of that specific buyer. If you want to see what that buyer is doing in the market, you need to use the bids. So the second approach is that we want to go with some relaxed version of this statement, saying that we don't rely too much on your bids. And so there are different ideas to implement this. One is that you use noisy bid. So this is like the ideas in differential privacy. So you get the bids, but you add noise to them. So each buyer would say, okay, my bids is not directly be used, but it's a noisy version of that one. So I don't have that much incentive to overbid or underbid. Or for instance, you can use the randomized algorithm. So in work of Mohammed Adel in what they do is that they use the exponential mechanism and ideas from differential privacy to somehow implement this idea. But this only works for the large markets and when the power of the buyers are limited. The second idea that we want to go with is so this is the path that we follow, is using the sensor bids. Just want to use some binary version of the bids. And this is inspired by a work of Karim et al., where they consider a single buyer. So when you have a single buyer, this notion of bidding becomes superfluous. It's just the action whether you want to get the item at this price or not. So it's a 0-1 response that you are getting. Now here we have multiple buyers, they submit bids, but still you can try to, instead of working with the bids, to work with some 0-1 version of it. So how do we implement this idea? So let's say you are at episode K and you want to estimate this preference vector beta for buyer I. So you do that with some optimization problem. This calligraphic L is just the minus log likelihood function for the allocation that you see in the previous round. So if you look at this expression, you see that BIT, the bits that are submitted from buyer I, doesn't appear anywhere in the formulation. You only have B index minus IT, which means that all the bits excluding the one that's coming from buyer I. And also you have QIT, the allocation, whether buyer I has won the auction in round T or not. Okay? So you are not working with BIT, you just look at the outcomes of the auction, whether that buyer you're targeting is the winner or not, and the bids coming from other buyers. Okay? And then this is the log likelihood that you get from the previous episode, and you want to estimate beta by minimizing this. Now, recall that we assumed that 1 minus f and f are log concave, so this is the place that we use this technical assumption, because this optimization becomes convex, and then you can easily, it's easier to analyze compared to the non-convex optimization. Any question on this? Okay, so in short, what you
no, it's in the logarithm conversion. The logarithm regret follows from this, so no, it's still going to get.
It follows from this. We'll get to that one. So I have one slide proof. But the important messages so far is that we are getting robustness against a strategic buyer, one, through this episodic structure of the policy, and using that the buyers are impatient. And the second one is that when we are trying to estimate the preference vector, we don't use the bits that are coming from that buyer. We just look at the outcomes of the actions. Okay, so this QIT are like this censored version. Now, the second question is, once you have these estimates, how do you set the reserve price? Okay. So to answer this question, let's make things simpler. Let's say you have a clairvoyant who exactly knows what are the preference vectors. And now the question is, what are the optimal reserve price? Now, the interesting observation here is that when you have a lazy second price auction, everything becomes decoupled. So when you want to see what's the optimal reserve price for buyer I, you can just assume that buyer I is the only buyer in the market. Just ignore everyone else. So you see that the revenue that you get would be Y times the probability that the valuation of that buyer is bigger than Y. So let's say you set the reserve price to Y. And then you can rewrite this expression in terms of the CDF of noise. And so, of course, you need to prove this proposition, but the message is that everything becomes decoupled, and then the optimal reserve price is given by this formulation.
But you still don't know you don't know exactly what that product is, right? You notice an error.
Sorry, sure.
Like you could not so that exactly because you don't know the dot product, right? Even the dots.
Yeah, this is a benchmark. Yeah, assuming that you know the beta, so that's going to be the optimal thing.
So the regret will be measured with respect to this guy.
Yeah. So if you know exactly what are the beta, these are the optimal reserve price. So the natural thing is that when you have some estimate, you just plug in the estimate in this formulation. So this is how you set the reserve price. And now how do we evaluate the performance of this policy is through the notion of regret. So the regret is how much you are losing compared to this clairvoyant who knows this preference vector. And we are computing, so this rev star is the revenue of the clairvoyant at time t, and this is the revenue of policy pi at time t, and you add them from 1 to capital T, so that's the cumulative expected revenue, the gap that you have. And we consider the worst case regret. So this is the maximum gap over all possible preference vectors and all the feature distribution that was unknown. Okay. So this is the benchmark that we have, the regret. And the theorem that we have is under this setting that f is known. With this policy, you can get a logarithmic regret. Okay. And one thing that I want to emphasize is that here, when I was defining the benchmark, I said that everything becomes decoupled, so let's focus on one buyer. But you see that in calculation here, I assume that the buyer is truthful. It's evaluation, not BIT. So in other words, the benchmark that we are considering is against the truthful buyers, and we want to compete with this benchmark. But the benchmark is quite strong, okay? Because we have the strategic buyer, but benchmark is defined against the truthful buyer. Okay. Now the proof is pretty long, so I try to do one slide proof, just to give you an idea of at least why this log factor is appearing. So There are three important factors in the regret: delta 1, delta 2, and delta 3. So delta 1 is just the estimation error. So assume that the buyers are truthful for a moment, so you don't need to deal with the strategic buyer. Even if the buyers are truthful, you still need to estimate this preference vector. And since these estimates are not exact, your reserve prices are not exactly optimal, and you get some regret from this one. So what we can show is that the difference between these two revenue, the squared one, this depends on the estimation of the preference vector. So it depends on your estimate beta hat and how it differs from the true parameter beta I.
Are you using anything about log concavity here? Or no? Because for any distribution, maybe translating the distribution can change reserve prices very much, right? Like if you don't know exactly where the distribution is placed.
Yeah, so we are using the log concavity.
Yeah, in that
Yeah.
step.
So the reason that I'm looking at this squared here, the squared of this one, is that when you start to write the difference between the revenue of the policy and the revenue of the benchmark, you can do just Taylor expansion. Now the first term of the Taylor would just eliminate because at the optimum the derivative is 0. And then you get the second order. Now the coefficient of that second order depends on the log concavity of the distribution that you said. But you need to deal with the squared of the R minus I. So the one say that the log concavity, the one that you said is the coefficient of the quadratic term. And so here I'm just splitting the sum over different episodes. So you have log T number of episodes because the lengths are doubled each time. And then what we can show is that this estimation error is like log of LK minus 1 times D over LK minus 1. So this is like the sample complexity that you get for the MLE.
Is it the sample complexity? What kind of assumption error? Sorry, what kind of assumption are you making on the process covariance matrix that generates the data actually here? The expectation of X transpose, something like this.
Yeah, so it's, okay, the second moment should be non-singular.
So it means that it's strictly positive definite.
Yeah, the second moment.
But don't you have like a dependence on the inverse minimal eigenvalue, something like this?
Yeah, so that's the constant thing. So these wiggles that I've sent, all of these equations are up to constant.
But this constant is really D, right?
No, it's not D.
This is a minimal eigenvalue of a metric.
Of a population covariance. So let's say you have.
But you're sorry, maybe you can take this offline. But you are normalizing things to be bounded in norm. So the expectation of X transpose is a matrix with trace norm 1, right?
Yeah.
And therefore the minimal eigenvalue is less than 1 over D. Right.
Okay, so I have that calculation. We can take it offline, but it's constant.
It's constant with D, but it's not constant with D.
No, constant with D.
It's also constant with D.
Yeah, all right, I can take it offline. But
that's it.
And okay, so this is the bound that you get on the estimation error. And then you have LK is the length of episode K. Now, these were just power of 2, so this is just 2, this 2, and then you get log T log times TD. Okay, so this is one term that is giving the logarithmic regret, and this is just coming from the estimation error, okay? Even when the buyers were truthful. The second effect is that, okay, now assume that you can exactly estimate the preference vectors beta I, but you have a strategic buyer. Okay. Now the revenue of the seller would be the maximum of the second highest bid and the reserve of the winner. Okay. Now because the buyers are strategic, they might underbid, they shade their bid, and so the second highest bid might go down because of this strategic bid. And that would adversely affect the revenue of the seller. So this is the second factor that we are capturing. Even if you can exactly estimate the beta. Okay. So for each of these factors, I'm fixing everything else, looking at one factor. So in the first one, I'm assuming everyone is truthful, just looking at the estimation error. In the second one, I'm assuming that you have no estimation error, but because of this strategic behavior, the second highest bid might go down. And the third one is that, let's say you can estimate the preference vectors, set the reserve prices to be the optimal one. So this set of RIT are equal to R star IT for all I. But because of this strategic behavior of the buyers, the winner of the auction might change. So you have, let's say, n numbers are equal to the optimal corresponding n numbers, but the winner is changing. So the reserve price of the winner might go down. This is, again, a subtle factor that we should capture. And then we bound each of these separately and add them together. Now, the second policy that we have is the stable CORP. Okay. So what's different from the setting that we considered so far is that the seller doesn't know exactly what the distribution of noise is, but has some ambiguity set calligraphic F that is the set of all possible distributions, and wants to come up with a policy that works uniformly well over this family. Now, what would be different from CORP? Let's see where we use the knowledge of F in the CORP policy. We use it in two parts. Part one was when we were trying to estimate the preference vectors. So we were forming this log likelihood function, and of course it depends on F. So we cannot use the log likelihood anymore. The second one was when we were setting the reserve prices. Again, it depends on the distribution F. So let's see what we can do. Since you don't know the distribution of noise F, you need to do more exploration compared to the core. Okay. So this is the high-level structure of this core. So again, it has some episodic structure. The length of the episodes are power of 2. But for each episode, you do exploration for this number of periods. So if you are in episode K, for LK to the power 2/3, you just do exploration. And exploration, I already explained what it means. You choose one buyer uniformly at random, set the price to be uniformly between 0 and B, and then set the reserve for the others to be infinite.
Just to make sure I understand, this LK will be something like
LK is 2 to
T.
the...
How does it depend on T, on the total time horizon?
Okay, so LK, it depends on what
Will be like
you're
T?
talking. So K goes up to log T.
No, I understand, but since you're expressing the regret in terms of the total number of rounds, so what's the length of this exploration? This is what I'm asking, as a function of T.
In total.
Yeah, as a function of T. I mean, I'm sure you have LK as a function of T, right? Would it be like a T to a 2/3?
Sum of 2 to the sum of...
Something like that.
Yeah.
All right. And that's why you get T to a 2/3.
So you give up the revenue on the exploration phases. But that's why you get T to the 2/3. And that's the dominant part in the regret. Okay. Okay. So let's start with how we estimate the preference vectors. We cannot form the log likelihood function anymore. So we just go with some quadratic fit. So we want to regress this allocation QIT based on the features that you have. Okay. And this B times N is a normalization. B is the bound on the valuation, and N is the number of buyers. And IK is just the exploration phase of episode K. Just give you short explanation why this factor should be Bn. So this QIT is just 0, 1. We are normalizing with Bn and then regressing that. So if you're familiar with these bounds and statistics, if you want to have a good procedure, good optimization to give you the estimate, you want to make the gradient of this loss function at the optimum to be very, very small. Okay. So one idea is to make the expectation of the gradient 0 and then use some concentration. So if I look at the expectation here, expectation is just this expression without 2. It's just under the square. And if I take the expectation, QIT, again, we are in the exploration. So with probability 1/n, I can choose buyer I. And then I set the reserve price for that guy to be uniformly between 0 and B. And the reserve price for the others are infinity. So the probability that the reserve price is at most VIT would be VIT over B because it's uniform between 0 and B. And then it's just algebra, you get the expectation would be VIT. And VIT is just XT times beta plus 0. So this gives you some unbiased estimate of VIT. So the gradient, the expected gradient at the optimal would vanish, and then you can show that the gradient itself is small. And the second question is how do we set the reserve prices? So here, to be fair, we also need to define the benchmark, because previously we were saying that F is known to the seller, so the benchmark has this leverage that knows the preference vectors a priori. Here, F is unknown, so we assume that also the benchmark doesn't know F, but has the ambiguity set calligraphic yes. And also knows exactly what are the preference vectors.
Isn't that a little bit of a weak benchmark? So in normal online learning, you don't necessarily know the distribution, but you always compete against the optimal for that particular distribution, right? Or you compete against somebody that knows what the optimal
distribution. You compete
distribution.
against the best optimal reserve prices here, but not the.
What do you mean?
My point is that normally you don't assume that the benchmark is also trying to do like a stable. So for instance, the whole idea of online learning is that you don't know what the distribution is, right?
So you're just arguing for the previous benchmark.
Right. Yeah. Should it be just the argmax of Y over the true distribution F?
Like, why does the ambiguity set of F actually come into
The
play?
motivation
Right?
is coming from the fact that the distribution F may actually change over time. So it's not like the distribution is fixed and then the benchmark knows that. Both benchmark and the algorithm doesn't know F, and because F can also vary over time, which can be function of different features or like things like that. That's kind of motivation.
Yeah, but that would be also a good benchmark if you assume that F is fixed across the time.
Yeah. So if F is fixed across the time, then yeah. The question is, should you be comparing against
Right.
the fixed
But
F?
then the min goes away, right? And then
Then the min goes away,
you
yeah.
just recover the previous benchmark.
Yeah.
Yeah, that's.
I mean, in particular for any ambiguity set F, there is some minimizer, and that is the benchmark with respect to the previous definition. Right, like you're actually competing against.
Oh yeah.
Right.
No, but it's too strange. It's so interesting because, for example, like to pick a broad class, like all normal distributions. But once you compete against all normal distributions, then you're competing with 0. Because it could be like the minimum normal distribution.
Actually, if you assume that the F, so if you assume that F is, for example, coming from normal distribution, and you don't know the parameter of that normal distribution, we don't include it here, but then you can relax this benchmark, remove the minimum, and try to, in your algorithm, try to learn the mu, the parameter of normal, and you get a square root t regression.
Okay, so that would be like maybe what they would say.
So the approach that so we wanted to come up with a fancier model, come up with a doubly robust algorithm, which is not only
Parametric assumption of the.
and instead of adding assumption, parametric assumption to the F, we wanted to say that there is ambiguity set because F may change over time, and we wanted to be robust against these changes in F.
I find a parametric even different, a bit more useful because if for to use that, I wouldn't know how to specify this answer to set. But I would like to say it's log normal. It's normal.
But for that one, we are gonna get a little exploratory.
And exploratory is the lower bound.
I was just wondering, can't you just sort of learn on the fly in this distribution based on the observation that you see, rather than trying to?
But you assume that it's non-parametric, you can fix.
Yeah.
Okay, so this is something that I thought about a little bit. So
You learn the cumulative distribution.
So the thing is that, okay, let's say the buyers are not strategic, so you see exactly what are the valuations, VAT, and then you can, let's say, fit OLS, the least square estimated preference vector, or subtract that from the valuation, and then look at the CDF of the residual.
Well, maybe you can do something even more basic, like for instance, you're doing like an exploration. Maybe, again, sorry, we can take this offline. If you're doing an exploration, you can set the reserve price very low in such a way that you can explore more, right? So you can sort of reconstruct the cumulative distribution.
But it's not clear to me what would be the regret. I mean, how much exploration you want to do.
Yeah, there's a trade-off, of course.
Yeah, so maybe to rephrase slightly, it would be interesting to see if you assume just a fixed non-parametric F, right? Kind of here you're coupling two things together. You're saying that F could be varying over time, right? And so because of that, you have this ambiguity set. But suppose I tell you that F is fixed, but I don't tell you what it is, right? Then the question of what the benchmark is very simple, right? It's the previous benchmark before, and the question is how well do you compete against it, right? And it feels, maybe at least to me, that you're coupling these things together, the dynamic change in F and the fact that you don't know it, and it'd just be interesting to see both sets of results. I think this would get to your question a little bit also. Right?
Yeah, a little bit. It depends over time, because XT, the noise may depend on the context. Is that correct? All right.
Okay. Okay, so going with this benchmark. So the way that we also set the reserve prices is, okay, we use just the estimates beta hat instead of beta, but you try to maximize the worst case revenue that you would get over all the distribution coming from this ambiguity set. And we call it stable CORP because it's stable against all the possible choices of this distribution coming from this family.
Is that hard to solve that problem, or in practice?
In practice?
Yeah.
You mean computational?
Yeah.
Yeah, it depends on what F.
Of what F is, but let's say over the space of all normal distributions, or.
Okay, so this is. Sorry. Okay. So I was talking to maybe our expert here. I don't know that much from GANs in the generative adversarial network, but this min-max formulation also appears there. I talked to a few people on how they solve this optimization over GAN, using those GANs, but I didn't formally proceed. But they have also the same formulation. They have their own method, at least heuristic, to solve this problem. I mean, this is a game between the two persons that you have over the network. Okay, and this is the regret bound that we get t to the 2/3. So if I want to just give you one sentence explanation why you get the log t regret when you know f, and you get t to the 2/3 here, is that when you know exactly what f is, you can use noise to get some free exploration. You can leverage, you can harness the exploration that this noise is doing, the randomness in noise. But here you don't know what the distribution is, so you need to do experimentation with these prices. So you want to play with random prices at this exploration. And that's why you can get log t there, because of the noise. So noise is actually helping. So that would be one suggestion. Even if you don't have noise in your model, you can add noise, and then you know what the distribution of noise is, and then you get the log t. I hope I made it more clear than confusing you more. Okay, so these are the takeaway messages. So we propose two policies for optimizing the personalized reserve price. We consider the contextual setting, so you have these features for the product, and you have the heterogeneous buyers in this setting. So one item could be evaluated differently by different buyers, and you have the strategic buyers who are frequently interacting with the seller and wants to maximize their long-term utility. We propose robust algorithm against this strategic buyer. The two important ingredients that helped us was first the episodic structure of the policy, and the second one was that we were using the censored bids, or the allocation, whether buyer I has won the auction or not, aligned with the bids coming from the other buyer. But we are not using directly the bids coming from that specific buyer. And then we have two policies, CORP and SCORP. The CORP policy was tailored to the setting that you know exactly what the distribution of the noise is, and you get the worst case regret of log T, log TT. And the second one is the SCORP policy. This is for the setting that the market noise distribution is not known. And we have this ambiguity set, and the worst case regret would be T to the 2/3. Okay, so with that one, I would conclude the talk.
So without incentives, what's the best known in each case? What are most problems?
What's
If you
the best
ignore,
known?
if you just assume buyers are truthful.
Truthful?
Yeah.
For the first one, I believe it's log T. It's log. Yeah, it's log T, log T. I think I can prove that. But for the other one, I'm not sure whether it's 2/3, T to the 2/3 is optimal. But my guess would be root T would be the lower one. Of course, it depends on the benchmark. So it's different benchmark.
How does it depend on N, on the number of bidders?
A very good question. So it depends linearly in N. And one open question is that if you are in the setting that the number of buyers is much bigger than the horizon of interest, so N is bigger than T, you would care about the dependency on N rather than T, and whether you can get log N, I don't know. But the current one is...
Well, if there are many, you can sort of cluster the buyers somehow.
Yeah.
It's a lot of things you can assume.
Yeah. So, if you cluster them into n prime number of clusters, and then so each of them is one buyer.
And that linear dependence comes from the fact that during exploration rounds,
Yes.
setting users.
Yeah.
Right.
I can give you more details since you have the work becomes because you're bounding the number of lives. How many times this strategic behavior has changed the outcome of the auction.
And in particular, this lets you do an analysis like we did in our
Yeah.
paper and not have to worry about
So you do that for one buyer and then you just add them. So that would be the order end.
You said you're using the other buyer's bids to set, sort of to learn.
Yeah.
What happens if how does it, what happens if buyers are not exactly ID? How?
The buyers are not.
They're not ID, so you're just using the.
Yeah.
For some
So
reason,
only the noise is coming from.
The noise is coming
the
from.
IT is only IID from the distribution, but you have this.
What happens if, so I guess that was my,
if the noise is not IID.
Yeah, so if buyers observe different noises, I guess, how do you happen to know how much the?
If I want to, so let's make the problem simpler. Let's say the preference vector is 0.
Right.
So you just have this ZIT and the valuation on top of it. So it's like that you have a market, the buyer, the bids are coming from some distribution F.
Yeah.
And you want to set the reserve price. But this work, Hamid and Yash did exactly this setting. And the result that they get, I think it depends on what's the distance between the virtual valuation.
Yeah, but they had that strong assumption of it.
on the distance between.
Yeah.
Like it's sort of an awkward
Yeah.
assumption.
They are smarter than me. So if there is something better, they should already solve it.
Thank you.